how do we define quantum technologies? Here we will define quantum technologies as exploiting deeply quantum mechanical phenomena, such as quantum superpositions and entanglement, for technological advantage over conventional methods. And there are typically three verticals in quantum technology, sometimes a fourth one. I will introduce them briefly here. Quantum computing, perhaps the most famous one, because there's a lot of media attention on it, a lot of media coverage. The goal of quantum computing is to implement algorithms with superior complexity scaling compared with what is possible with classical machines. People are also interested in quantum cryptography, which can enable provably secure cryptographic key distribution for safe communication between agents. The third pillar or vertical of quantum technologies or application of quantum technology is quantum sensing. Here we're talking about measurements of physical quantities with superior precision over conventional techniques. And finally, perhaps the less known one, but quickly growing application of quantum technology is quantum random number generation. Here, the goal have been breakthroughs in quantum error correction. Proof of principle demonstrations have been made, for example, at Google or at a Canadian company called Nanoacademic, where error correction has been demonstrated not to the level that is needed for fault tolerance, but in a proof of principle experiment has been shown that better error rates can be obtained, or lower error rates can be obtained with logical qubits than with physical qubits. So this convinced a lot of people that fault-tolerant quantum computing is in principle feasible. However, to truly get a fault-tolerant and useful quantum computer that is unambiguously, demonstrably useful, we would need to scale up to millions of physical qubits, and we're orders of magnitude away from that objective skill still. So how do we get there? Sorry, just loading the next slide. Okay, yeah, there are many challenges actually. So first of all, fidelity. We have to optimize the gate fidelities, the initialization, readout fidelities, all at the same time. It's very difficult to have good fidelities across all operations. There are materials issues. So defects can appear. They're deeply tied with the material science. This should be an interesting field for all of the DFT people here. I think there's a lot of potential to explore material science for quantum technologies. And in particular, those materials issues, they lead to reproducibility issues. You can have device-to-device variability. For a few qubit system, that's not really a problem. You can engineer your way around the problem, but if you scale to millions of qubits, then this will become very difficult. And this creates fabrication costs and fabrication times. These fabrication delays and costs are a problem when everything is based on trial and error. So our opinion at Nanoacademic is that in the long run, trial and error will not work, and I think everybody kind of agrees with this already. And even educated guesses based on even very good analytic models of those devices will probably not suffice either, because we need to engineer highly isolated systems to protect them from noise, but also those systems must be able to interact in a controlled way. So that's a very difficult engineering challenge. Our vision is that computer-aided design software can help to get there. Just like in classical electronics industry, engineers have been using TCAD, technology computer-aided design software, for decades. And in TCAD, the idea to start from a real device that is industrially relevant, such as a MOS device, create a 3D model with an arbitrary topology, and solve some classical or semi-classical physics models to get experimentally relevant performance metrics, such as an IV curve for a transistor. In quantum technology computer-aided design, so QTCAD, we again start from a real device that is industrially relevant. It could look very much like a transistor. In fact, spin qubits are fabricated with the same techniques, but now we need to solve for much more deeply quantum mechanical models that include entanglement, superpositions, and many other phenomena that are absent from conventional TCAD software. And then the users, at the end of the day, will care about very different performance metrics. They don't necessarily care so much about current voltage characteristics, but they care a lot about how fast can I do a quantum logic gate. So can we model Rabi oscillations, for example, in these TCAD software? So the idea here is that conventional TCAD software is not, while excellent for its applications, is not suitable to quantum hardware design. So we have to develop new software capabilities to really accurately model the performance metrics that matter to quantum technologies. So our competitive advantage as Nanoacademic in that respect, we think we have three main broad categories of advantages. The first one is we developed our own adaptive meshing algorithms. This is true in many TCAD software, but to achieve user-defined accuracy targets. But our adaptive meshing algorithms have a special tweak for spin qubits and semiconductors that enable us to achieve convergence of the electrostatics at cryogenic temperature below 1 Kelvin. And that is difficult using conventional TCAD software. Another important advantage that we have is atomistic models. We have tight binding solvers that can solve up to 1 million atoms embedded into QTCAD for basic semiconductor materials, silicon, germanium, silicon oxide, silicon, germanium alloys that are really relevant to spin qubits and can model quantum dots very accurately. But in addition, we have these software packages, Rescue and NanoDecal. These are separate products from QTCAD, but they enable ab initio modeling of complex materials, including AI acceleration for up to 10,000 atoms. And this can be used to model many features of the materials that are used in quantum hardware. And this can be used to extract parameters, for example, that will go into QTCAD. And the final competitive advantage is we have these quantum mechanical models that are encoded directly into QTCAD that are absent from conventional TCAD software. That's an absolute necessity for qubit modeling. So with this introduction done, I would like to describe some use cases of QTCAD. First, who are our users and collaborators? We have users, typically scientists and engineers in academic, government, and industrial environments. We developed QTCAD thanks to several R&D grants from the governments of Canada and Quebec here. And we have R&D partners and customers across North America, Europe, and Asia. I'm showing a subset of those R&D partners and customers, but you can see we work with ST Microelectronics for a long time now. There are also startups that are developing quantum technologies such as Equal One, Quobly, Quantum Motion that use our software. We collaborated with Nanoacademic to develop our superconducting qubit modeling software. And we also collaborated with the National Research Council in Canada to develop a lot of QTCAD and QTCAD use cases. So we have commercial users of QTCAD from industry and academia since 2023. And of course, for our DFT software, this is a much longer story that dates back to 2007 or 2008, the foundation of the company. There's a growing list of publications using QTCAD. You can find links to those publications on the Nanoacademic website. Some of the publications come from ourselves, but in the last year, actually, our users got better than us at publishing. So with QTCAD, they now have several publications in high-impact journals such as Physical Review Letters or Applied Physics Letters or PRX, Nature Communications, Scientific Reports. And in those publications, you will find some QTCAD simulations. So we have now more than 25 scientific publications and preprints using QTCAD, and this doubled since last year. So we think there's a lot of momentum there. A quick overview of unique features of QTCAD. As mentioned, we're able to converge electrostatics at cryogenic temperature for spin qubits. So here I'm talking about spin qubits now. We have effective mass and K.P solvers to find the electronic structures of electrons and holes in quantum dots. We have many-body and master equation solvers for charge stability diagram calculations to evaluate if certain gate bias configurations and geometries able to capture 0, 1, 2, or 3 electrons, for instance. We have valley coupling calculation feature, which is absolutely important for silicon-based quantum dots, advanced spin physics, quantum well physics, and a Rabi oscillation module to predict how fast can quantum logic gates be done in a given system. We also have, for double quantum dot or multiple quantum dot, the capability to calculate the strength of tunnel coupling and exchange. These are resources for 2-qubit gates in particular, or even single qubit gates and some exchange-based spin qubits. So that's very important in order to assess how fast a quantum computer could be based on spin qubits. We have non-equilibrium Green's functions module to calculate tunneling, sequential tunneling currents through quantum dots, and many additional features. I'd like to mention that we have a free 30-day trial version available online. We released QTCAD 2.1 last week with many new features. Since QTCAD 2.0, we also support atomistic simulations directly in QTCAD for specific materials, namely silicon, germanium, silicon oxide, silicon germanium alloys. We'll add materials as we keep developing the software. But the idea here is that we're able to do multi-scale simulations where we use continuum models to model the electrostatics of the device at the micron scale. But at the nanometer scale, we can zoom in the quantum dot region and model the quantum dot atom by atom and find the electronic structure of the quantum dot with atomic resolution. And this is absolutely crucial to study accurately Valley physics, spin-orbit coupling, G-tensor calculation, strain, and eventually shuttling calculations, and device-to-device variability phenomena arising from rough interfaces, random alloying in those devices, and also some potential for individual dopant impacts. So this will be extremely important as the spin qubit technology evolves and scales up, because these device-to-device variability effects are an obstacle to scaling. So studying them with computational methods is absolutely crucial. When it comes to superconducting qubits, it is possible since QTCAD 2.0 to model superconducting circuits using QTCAD. We will see an example in this presentation. We can do capacitance matrix and Maxwell eigenmode calculations, but also with nanodecal and rescue, it is possible to do atomistic simulations of Josephson junctions. So because we can handle both the atomistic scale and the macroscopic scale of capacitors and resonators, we have the capability with Nanoacademic software to calculate all parameters, capacitance matrices, Maxwell eigenmodes, couplings, Josephson energies, all relevant parameters that come into the Hamiltonian that describe QPUs, superconducting qubit QPUs. Once these Hamiltonians are obtained, it's possible using open source software such as SC Qubits or QTIP to calculate chip performance figures of merit. I'd like to go into more concrete use cases. Last year at the March meeting in Anaheim, our users Equal1 announced that they had built this new quantum computer called Bell1, which contains a 6-qubit quantum chip, 6-qubit QPU, and this was operated live at the meeting, at the March meeting. The computer is small enough to fit in a standard data center rack and can plug in a standard 120-volt outlet, which makes it unique. Very few quantum computers can be operated this way. And I'd like to mention, if you go into the paper, it's now a preprint, but eventually we hope will be published very soon. If you go to the preprint link and you look at figure 1, the way they explain how the quantum chip works is partly thanks to a QTCAD simulation. So this is proof that they're using QTCAD in their day-to-day design of chips that go into actual quantum computers that are now commercial. I'd like to mention another concrete use case that came out from this company, Equal1 again. This was published in scientific reports, or is accepted in scientific reports. The manuscript is available. It will be officially published, I think, in a matter of days, in which the same company, Equal1, studied Global Foundries 22 nanometer poly-depleted silicon application techniques are the same. Everything was fabricated by Global Foundries with standard techniques, but the topology was modified to create a quantum dot array. And the quantum dot array was studied both experimentally and measured experimentally. They measured the so-called lever arm. So they computed with QTCAD all of the energy levels of the quantum dots in this array and found how do they behave as a function of gate biases. So you have an electrostatic gate bias that controls the energy levels. And this lever arm tells you by how many electron volts do the energy level of the quantum dot shift when you apply 1 volt on a given gate. So this tells you how much control you have on your quantum dots electrostatically. So this was done using QTCAD. They found a lever arm of 0.226 electron volts per volt, which compares within a few percents 0.27 electron volts per volt measured experimentally. So this not only shows that you can actually model these systems, but you can model them quantitatively with QTCAD. And the fact that they could get the same lever arm also means that the quantum dots that they got were formed electrostatically as expected from the design, which is non-trivial. Sometimes people get spurious quantum dots in those kind of devices. So this really shows that they're doing what they want. And eventually, as they scale up, then they will be able to use the software to skip a lot of trial and error. So this was released, this was accepted in scientific reports very recently. Use case number 2 for superconducting qubits. This is a collaboration with Nanoacademic, a company based in Sherbrooke, Canada. We modeled their systems. Here is a transmon in a cavity. We calculated the capacitance matrix of the system and compared to their own values, their own reference values successfully. This calculation could be done on the laptop within minutes. We did a similar capacitance matrix extraction for an X-mon qubit provided by another Canadian company called Red Blue Quantum. And we also did Maxwell eigenmode calculations. So in the hands-on session, I will show you how to do this kind of calculation with QTCAD and Qiskit Metal, which is a GUI for those kind of superconducting qubit simulations. I also want to briefly mention that QTCAD is used not only in research and engineering, but also increasingly in education. We have educational licenses available, and this has been used in teaching at Politecnico di Torino in Italy, and more recently at University of Toronto in an electrical engineering class on quantum hardware design. So let's go into the more live demonstrations. Spin qubits and semiconductors first. We will concentrate on a simple simplification of an FDSOI device to make the simulations run faster and make the presentation more pedagogical. How this will work is we will start from a layout that describes the structure. So I'll open the layout in K-layout. We have it here. There are multiple layers that define the structure. I will hide some of them. First, the domain. This is just a rectangle that describes the simulation domain. So you can see the dimensions here. It's in the hundreds of nanometers, about 100 nanometer. And this is, of course, a subset of the full chip, but we're interested in the region where the quantum dot is going to be formed. There will be a film layer, which describes 4 regions. Here's the source, the drain, the channel, and the shallow trans insulators on the sides. If I double click on the region, unfortunately, right before this presentation, my Windows settings somehow randomly changed, so it's very difficult to see the text. I will just read it aloud. We can see here user properties. If I click on it, there's text editor or table. There's a key called name, and the value is channel. So this is a name for the 2D shape that will be used later to assign a specific material to the channel in the structure. Likewise, if we go here in the user properties and table, the name is the drain. So we will have a source, a drain, a channel, and some insulators on the side to define the quantum dot. We also have top gates. These are metallic top gates that are used to control the barrier, the potential barriers of the quantum dots, and also the depth of the quantum well that forms the dots. So if I go back to the presentation, this is what is described here. We will create a 3D geometry that we will be able to visualize as well in a Jupyter notebook. The 3D geometry is shown here. We have the source in magenta, the drain in dark blue, with dopants concentrations of 10 to the 20 centimeters minus 3 for the source and drain, so strongly doped source and drain. We have an undoped silicon channel. We have barrier gate 1, barrier gate 2, and plunger gate to control the quantum dot electrostatically. And we have an additional back gate because this is a FDSOI structure that can also be used as electrostatic control of the quantum dot. Here I'm showing a 2D slice like this to clarify the geometry. We have silicon in pale blue. We have a hafnium oxide layer here that's 2 nanometer thick, and we have silicon oxide all around. So quantum confinement of electrons in this XZ plane is provided by the band offset between the silicon and the surrounding oxides, whereas quantum confinement along the transport direction, so along Y, will be provided by these electrostatic gates. So what will be solved in this tutorial? We will do a very basic simulation. There are many more unique features in QTCAD as mentioned before, but nearly every QTCAD simulation for spin qubits starts with these steps of solving for the electrostatics, first using the nonlinear Poisson equation. So this is Poisson's equation. Pi is the electric potential, epsilon is the dielectric constant, Q is the fundamental electric charge, and this here represents the charge densities from the charge carriers in the source and drain, and also from the dopants. This is a nonlinear Poisson equation because the carrier concentrations in the source and drain depend themselves on the band bending. They depend on the electric potential through the conduction and valence band edges. Once we have converged this nonlinear Poisson equation and found the electrostatic potential throughout the structure, this defines the confinement potential. And then we can find the electronic structure of the quantum dot by solving an effective mass Schrodinger's equation for it. It's defined like this. So f of r here is the envelope function. This is equivalent of a wave function at microscopic scales that are much longer than the atomic spacing. This is a notoriously difficult problem to solve because the nonlinearities associated with the electron and hole charges are much stronger at cryogenic temperatures. So adaptive meshing may be needed for robust convergence, and that's something we describe in this paper. So that being said, let's jump into the code and do the demo. So I'm going to open this interface to our one of our workstations at the company. Here I'm showing. Excuse me, is someone asking a question? There's someone whose mic is open, I think. No? Okay. Thanks. So we have 3 Jupyter notebooks open here. So I didn't mention it in the slides, but QTCAD is controlled through a Python API, and the most pedagogical way to teach how the Python API works is through Jupyter notebooks, which are interactive.
Yes. Yeah.
Okay, perfect. Thanks a lot for letting me know. This would have been embarrassing if I kept talking. Okay, so we have these 3 notebooks. The first one here, Generate Mesh, is going to be about generating the 3D structure that I just described. The second one is going to be this Poisson and Schrödinger simulation. And the third one is going to be the lever arm calculation. We won't have time to go through the whole, but please feel free to reach out if you want the notebooks. We can provide them, no problem. And this is how to get these lever arms that equal 1 GUT for their own more complex device. So how does this work? So we already looked at the layout. And here we're going to use a new feature of QTCAD that was just released last week, which is QTCAD Builder, which is an automated way to create 3D structures in a scriptable form from layouts directly. So we're going to import Builder, and we're going to set some paths to an OASIS file that contain the layout, and paths to output mesh and geometry files that we will produce thanks to the layout. We'll also define the growth axis dimensions. So the gate oxide thickness is going to be 2 nanometers. The film thickness, where the quantum dot will be 10 nanometers, and the buried oxide thickness will be 10 nanometers as well. We will define a basic mesh characteristic length, which will be very coarse to start with, because we'll start with a coarse mesh and then refine using adaptive meshing. A coarse mesh with 10 nanometer characteristic length. And then we will initialize a builder object using this builder command, and we will load the layout here. So here I loaded the OASIS file from the layout, which I just showed. And then we can print the mask 3, which contains essentially all of the layers we described. So domain, dot region, film, top gates, and the names of all the polygons contained in those layers. So domain, spacer 1, source, spacer 2, drain, channel, and then the names of the gates. Plunger gate, which is used to control the energy levels of the quantum dot, and barrier gate 1 and barrier gate 2, which are used to control how isolated the quantum dot is from the source and drain. And then we can grow a structure layer by layer from bottom to top. And we will do this step by step. So we start by using, we say builder.useMask. We use the domain mask to set up the size of the simulation domain. And we also set the characteristic length using this command. And then we will grow the buried oxide layer and visualize. So how we do this, we take the builder object, we copy the mask that's called box. We rename the shape into box, and we extrude by the box thickness, box being the buried oxide. And then we can view. This will call a Gmesh prompt. Do you see the prompt?
Yes. Definitely.
Yeah, perfect. So this is just displaying the buried oxide. This is just a prism, right? I will close the window, and then we can keep growing layer by layer. After growing the oxide, we can grow the film using the film mask, using the same procedure. Use mask film, extrude by the film thickness, and then view. So you can see now we have a fairly more complex 3D geometry where we can see the source, the drain, the channel, and the shallow trench insulators on the sides. We can then grow the gate oxide using similar commands. So we have a slightly thinner region here. And finally, we can deposit the gates using the top gates mask, using the add surface command. And now we can see rectangles that correspond to those gates. So I will do is I'll do mesh in 3D tools, options, and I will show the 2D element faces to see, you can see different colors for the various gates on top. Okay. We can also add the back gate. The back gate is the size of the domain, so we're going to use the mask domain. We're going to set the position at which to apply the back gate at 0, which is where we started along the z-axis. And we're going to copy the mask called back gate and add the surface. And finally, we can mesh, save, and visualize the final result. So we have this 3D structure and 3D mesh for our FDSOI quantum dot. I'd like to mention we only use the most basic features of Builder, extrusion, but Builder also supports etching, growth, and many other 3D operations. So fairly complex geometries with overlapping gates can be made now with Builder. After creating the 3D structure, it's time to solve the electrostatics of the structure. We're going to go into this second notebook. We will import basic QTCAD modules such as physical constants, materials module, analysis tools to plot, input and output tools to save and load files, mesh modules, device class, which is used to define the physical device with various materials, various boundary conditions on the mesh, solver classes for Poisson and Schrödinger solvers, and also solver parameters classes to tune the solver, the parameters of those solvers. So we import all this, and then we will set up the device. So we have gate biases. So I mentioned already all of those electrostatic gates. These define the voltages we will define. These are simply variables that we can change later on. So they define the biases in volts. I will define paths to the mesh, the geometry, and output files. And then we can load the mesh using this capital mesh command. So this is a class. We're creating an object called mesh. We're setting the characteristic length of the mesh, so the units of length to be 10 to the minus 9, so one nanometer. And then we load the mesh from the path. So we can see the mesh characteristics here. For example, the total number of nodes is 1,000. So that's a very coarse mesh to start with. And then we instantiate the device. The device is the most important object in QTCAD. It contains all of the physics information that is going to be stored on the mesh. So we define the device, instantiate it using the mesh, and we're going to set that the confined carriers, so the carriers for which we want to look at quantum confinement here are electrons rather than holes. And we're going to set the temperature to 0.1 Kelvin, so that's cryogenic temperature operation. We can then define the device regions. So based on the labels that we had in our layout, we have various 3D regions for the buried oxide, spacers 1 and 2, so the shallow trench isolators on the sides, the gate oxide, the channel, the source, and the drain. So using this new region command, we can set the materials, for example, SiO2 or hafnium oxide or silicon, but also the doping concentrations. And since we're using SI units, we take the values in centimeters minus 3, multiply by 10 to the 6 to get meters minus 3. So we define all of those regions. We define the boundary conditions. We have gate boundary conditions. This is identical to TCAD software in terms of boundary conditions. We have the gate boundary conditions with a work function, who we're taking it to be mid-gap work function of silicon. And we apply all of our barrier gate and plunger gate and backgate biases here. We can then visualize the device. Since last week in QTCAD 2.1, we have a brand new device visualizer. So we have this command device.show, which enables inside the Jupyter notebook to visualize the structure in 3D. This is useful for plotting, but also for debugging. If there was any mislabeling of regions, we would see it here. So I'm going to show the boundaries. We have the plunger gate boundary. We can make it disappear and reappear like this. We have barrier gate 2, barrier gate 1, and the back gate at the bottom. And then we can also hide and show various regions based on their labels. For example, the source. But we also can toggle between materials. So I can decide, for example, to hide all the oxides. And then we can clearly see the silicon source, channel, and drain, and the gates that are going to be used to control the quantum dot electrostatically. The next step is to set what we call a quantum dot region. We want this region to be somewhere in the channel below the barrier gates and the plunger gate. What do we mean by the quantum dot region? It is a region in which we will remove all classical charges because we want to model these charges quantum mechanically using our Schrodinger solver. It is also a region where typically we want a finer mesh. So how do we set this up? We use this channel equals submesh command to grab just the channel region, but we want not only the channel region, but a part of the oxide that wraps around the channel, because we want to model quantum confinement arising from the band offset between the silicon and silicon oxides. So what we do here is we grab the channel and we define XYZ coordinates of the channel corners, and then we expand by various buffers to take into account the oxides. Once we have defined this dot region, so let me make sure I ran these cells properly. I'm going to run these two. Then we can set up the nonlinear Poisson solver. Here we are going to use the adaptive mesh. These params Poisson, these are parameters of the solvers. Normally, we can run without that using default parameters.
Yes.
Excuse me, someone has his mic on. Yeah, thank you. Here we're using some custom parameters that I chose for the simulation to run quicker for demonstration purposes. But the idea is you have this Poisson solver params object, you can instantiate and you can modify the convergence threshold, you can modify the refinement factor to control how fast we refine, the number of iterations, maximum number of iterations, the name of the name of the file in which we'll save the mesh, etc. Then we can instantiate the Poisson solver on the device with the solver parameters we chose, and using the geometry file that was produced with the generate mesh script. And then to run the solver is very simple. You call the solve method of the solver object. We're going to run it now. And for this simple device, it runs pretty fast. So we already solved for the coarse initial mesh in less than a second, I believe. The mesh is being refined right now to ensure convergence and to ensure sufficient precision. We're loading the mesh right now. And now we're running for a finer mesh. Okay. The iterations are going to fly by pretty quickly, 1 second per iteration. And after 18 iterations, 33 seconds, we converged. So we can save the electric potential for visualization. We can also do a line cut of the conduction band edge along the channel. And here we can see the line cut. Because we have very strong doping in the source and drain, the conduction band edge goes well below the Fermi level, which is at 0 on this plot. We have beautiful barriers associated with the barrier gates, and we have a well associated with a plunger gate. And now we have a quantum well. The question is, can we really get bound states in that quantum well? And to answer that question, we need to solve Schrodinger's equation in the dot region. I'd like to mention we can also save the electrostatic properties in VTU format to visualize, for example, in ParaView in 3D, the conduction band edge. How to solve Schrodinger's equation? We create a submesh object, which corresponds to the dot region, which we defined earlier. It's a subregion of the whole mesh. And we define, likewise, Schrödinger solver. We are going to set the tolerance of the solver to 1 micro electron volts. We can then set the confinement potential from the electric potential obtained from Poisson solver using set V from phi. And then we set a sub-device, which is corresponding to the submesh, so the small region where the dot is expected to be. Instantiate and run a Schrödinger solver. Because I'm running on multiple cores right now, in only 2 seconds, I got the results. On my laptop, it's something like 30 seconds. We can print the energy levels of the quantum dot, and we can also use this analyze dot method to print geometric properties of the quantum dot, namely its position, standard deviation of the ground state, and size of the quantum dot in SI units. So here we have a quantum dot that is 32 nanometers by 15 nanometers by 3 nanometers, roughly. And then we can save the wave functions in VTU format and visualize the wave function in 3D, in ParaView. So here I'm showing the ground state wave function in the quantum dot region. I can switch and also show the first excited state, for instance, which is along another axis. So what I'll do, I'll show the second excited state. Actually, they're both on the second different axis. So let's do first excited state. We're going to do a different clip. We're going to clip along the Y plane, apply. And then show first excited state and second excited state. All right. We can also plot slices inside the notebook for these states in the channel plane. And finally, before I jump into superconducting qubits, we have a notebook also for lever-arm extraction. We have notebooks for Rabi oscillations, for many other steps. What I wanted to show here, we can also get, by sweeping plunger gate biases, the behavior of the energy levels as a function of the plunger gate bias, and extract a lever arm of 0.86 electron volts per volt. So this is very similar to the calculation that was done in equal 1 use case, but for a slightly simplified and different geometry. This being done, I have some time remaining to describe the superconducting qubit solver. I will need to go a bit faster there because we have only 15 scheduled minutes. But what I want to say is that we have an interface with Qiskit Metal, which contains a GUI. We have a new tutorial, a notebook that is available on demand that is not on our website. Please feel free to reach out if you want it. What we will do here is to model a qubit coupled to a microwave resonator. So this is an X-mount qubit. This is a microwave resonator, and this part here is a coupler. Qiskit Metal has a GUI, but also a library of quantum components. For example, X-mount, pocket transmons, interdigitated transmons, various types of resonators. And in the GUI, it's possible to define the quantum chip that one wants to model. But Qiskit Metal does not do the simulations by itself. It needs renderers. there are multiple renderers, but we developed a QTCAD renderer recently. It is now available. We will do the simulation of the X-mount coupled to a resonator. We will calculate the so-called capacitance matrix, which is very important to calculate the charging energy of the transmon. So this here is the transmon Hamiltonian. There are two main parameters, the charging energy and the Josephson energy. Josephson energy is typically given as a boundary parameter. People fab the Josephson junctions and measure EJ and tell you what it is. But we can also model EJ using nanodecal. If you're interested in this, please reach out to us. The charging energy is obtained from the capacitance matrix calculation. It is defined as E squared over 2 times CT, where CT is the total capacitance. In this specific example, this total capacitance is given by this formula in terms of various components of the capacitance matrix, which will be calculated in the tutorial. Knowing the charging energy is very important because the charging energy, along with the Josephson energy, defines the energy splitting of the qubit. It defines, in fact, the whole transmon energy level spectrum. So let's go into the notebook. Which is in a different tab. So the notebook is fairly detailed. It describes what is Qiskit metal. It describes the physics of the structure. Let me scroll down. There's a preamble in which we can load all of the relevant Qiskit metal modules and QTCAD modules. I will run this cell. We can define a name for the simulation. We can set number of Maxwell eigenmodes to compute. I will go back into Maxwell eigenmodes later. We can set relative tolerances for the capacitance and eigenmode extraction. These are set to be fairly high in the simulation to be able to run faster. We can set minimum and maximum characteristic lengths of the starting mesh and say we want to use adaptive mesh refinement. We can set the paths to the output directory, geometry file, and mesh files that we're going to save, and instantiate a design object that will be used by Qiskit metal. So as mentioned, Qiskit metal has a GUI, but also a Python API. In this notebook, we define the quantum components, Xmon, resonator, and their properties, their geometry, entirely using dictionaries. But I will show you also that this can be done in the Qiskit metal GUI by launching the GUI. So this is what it looks like. You have various components. Qubit 1, which is here. You have a coupler between qubit 1 and the meandered resonator. You have a connection between the resonator and the ground. And you have the coplanar waveguide resonator itself, defined here. I want to show you there's a library of components to select from, various types of qubits, squid loop, star qubit, transmount, concentric, etc. There are various types of resonators as well. And it's possible also, suppose I select a quantum component like the transmon, it's possible to go in this window here. I won't do it because I don't want to mess up the simulation, but we can tune the parameters like the width of the cross, the length of the cross. Any parameter can be tuned here, and the model will respond live inside the GUI. So I'm going to close the window, and I will not save any change because I don't want it to affect the rest. So Qiskit metal creates 2D layouts, but now for electromagnetic simulations, we need a 3D model. So how does this work? There's a GMesh renderer, which enables to create 3D models. And this all goes through our QTCAD renderer. So in this cell, we show how to set the capacitance matrix calculation options, for example, the relative tolerance, some options for the eigenmode calculation, the number of modes, the tolerance. And then we can set some options for the QTCAD renderer. Do we use adaptive meshing? Where do we save the files? The options of the capacitance and Maxwell eigenmode solvers. And then we can instantiate a QTCAD renderer object that is used to run the calculations using the Qiskit metal design. Then we can create the geometry from the designs using the render design function. And after this is done, we can launch the GUI of GMesh to show the 3D structure. So we can recognize the 2D layout here, but now we really have a 3D structure that accounts for, say, a chip that supports the 2D layout. So you would have aluminum layers on top of a given material, and then you have vacuum on both sides. Once this is done, it's possible to mesh the device and show it. It's not very necessary because we won't see much when the mesh is on top of everything because our device is inside. And to do the capacitance extraction, how this is done, very simple. You can export some parameters. That's an optional step, actually. The most important part is just this. QTCAD renderer.run QTCAD and solve for capacitance. This is a lengthy calculation, so I will not run it live. On this machine, right before the meeting, the calculation took about half an hour. This is because the model is fairly complex with lots of meanders and everything, and we use adaptive meshing, so we refine progressively here 7 times to achieve the required tolerance. But at the end of the day, we can display the capacitance matrix, and that is shown here. And these are the parameters that go into the formula for the charging energy of the transmon. So this total capacitance here. So using that formula, we can calculate the capacitive, the effective capacitance of the XMON and the capacitive energy of the transmon here around 200 megahertz, which is typical. Finally, I'd like to quickly show you that it's possible to also do Maxwell eigenmode simulations with QTCAD. Why is this useful? Well, the Maxwell eigenmode can tell you about the qubit frequency and the resonator frequency. So here in this design, we're solving Maxwell equation in frequency domain using QTCAD. We can find eigenmode number 0 has its electric field mostly within the transmon, whereas eigenmode 1 has its electric field mostly in the microwave resonator. So the frequencies of these eigenmodes tell you the qubit frequency and the resonator frequency. And these are useful for many reasons. First of all, these are in themselves parameters you need to know in a given design, but also using these parameters and the capacitance matrix, you can calculate the qubit resonator coupling, which is a key parameter to describe qubit readout and also 2 qubit gates in the situations where the resonator could be used, for example, as a quantum bus to couple 2 distant qubits. I will briefly show you in the notebook that this can be done. I want to leave some time for the questions, so I will just scroll through and show you the final results. But you can see this is not much more complicated calculation than before. You just run QTCAD by solving for eigs instead of cap. And then at the end of the day, you do the simulation. This took a little bit less, maybe 700 seconds, so that's maybe a little bit less than 15 minutes. We get the eigenvalues and eigenmodes, and then you can do this plot eigenmodes command to view eigenmode 1, eigenmode 2, and then the higher energy eigenmodes can also be displayed if you want. And the coupling constant can be calculated using the formula. This is simply an analytic formula, so you can easily write it in Python. And here we get 58 megahertz, which is a little bit less than the typical value of 100 megahertz, which is a typical target in this field, but the right order of magnitude. So one could keep iterating through the design to kind of optimize the geometries to get a better coupling constant. So with this, I'd like to conclude. Let me go back to the slides. In summary, we have developed multiscale 3D TCAD simulation workflows for spin qubits and semiconductors and superconducting circuits. I didn't have time to show that, but for spin qubits and semiconductors, we can even do atomistic simulation within the same platform. Quantitative predictions have been validated in several use cases. I've shown a bunch of them, but there are more in the literature. We have simplified live demonstrations based on these use cases. And future directions will involve, of course, more use cases of multiscale methods and experimental data with R&D partners. And we aim to also scale up to larger qubit systems. Our ambition is within the next few years to be able to model systems with 10 or more qubits. Thank you very much for for listening, and I'm happy to take any question you may have now.
So, dear Dr. Félix, thank you for your nice talk on your QTCAD software. Definitely, it's quite interesting talk today. So now I would like to request to our participants, please you can ask your questions to our speaker, and then later on whatever your queries will be there, I will be here to help you. So please put your questions. You can unmute your mic or you can put your questions in the chat box.
Yeah, definitely. Thank you. Wonderful presentation. Uday from Calcutta University, online group. So particularly what I do, I design superconducting qubit. Okay. So in in this year, I have explored like console, Keysight, ADS, and Metal, and all those platforms available. SC qubit also, I have explored that one. So I want to know what is the accuracy of your model, like extracting the eigenmodes.
In terms of relative error?
Yeah, relative error. Yeah, definitely.
Yeah, this really depends on your mesh. So the simulation I showed has pretty high tolerance because we wanted it to run fast, maybe 1% tolerance. You can do lower if you want, if you're more patient. So it's really just a question of how much memory you have to get a very fine mesh, and how patient you are to wait for the refinements.
Another questions I do have that whenever I have designed a large superconducting chip in Qiskit metal and try to simulate it, what happened that metal crashes? Okay, that GUI crashes. Okay, that thing happened. So is there any issues with this too, or just modeling just few?
Okay. Yeah, of course, for the general audience, I mean, you're already aware of this, but Qiskit Metal is not developed by us. It was developed by IBM in the last few years. IBM stopped supporting it, but it's maintained by the community, which means, there could be instances where this kind of things happen. And for now, we're not maintaining it ourselves. So there's not much we can do about it. But it is a very good tool. It just sometimes has little things like this.
Yeah, definitely. But if I have a GDS file, that GDS2 file of my design, so can I do the simulation using QTCAD?
So directly with QTCAD without passing through metal?
Yeah, without passing through metal.
Okay, if you want to avoid passing through metal entirely, what you can do is create the model in GMesh.
Okay.
And then you would get rid of that step. Whereas if you can you could try to see if Builder supports the geometric operations you need. Actually, it would be a good way. If you want to follow up with us, you can ask us the question directly. The idea would be you start from the GDS file and try to do some extrusions to create the model that you want in 3D. Maybe this is possible, and then you would avoid passing through metal entirely. I cannot promise you because we've never done this. In principle, it could be tried though.
Okay, then I will definitely reach you. Should I mail you?
You can mail us, or there is also a customer service desk that's available on our website. This might be a faster method to get an answer because we have customer support people who will respond faster than the CEO. I guess, Anil, do you have the link for the customer service desk? Maybe I can just share it here, actually.
Yeah, definitely. Yeah, that will be great.
I will send the link, Félix, no problem.
Sir. Hello, sir. Can we use AI to enhance gate fidelity for superconducting qubits? Am I audible, sir? Hello. Sir.
Yeah, Mr. Kumar, please patient a second. Félix will be back in a short while. Thank you.
Okay.
Yeah, sir, please
I'm
wait
back.
few seconds.
I'm back.
Yeah, Felix is
Sorry.
joining.
Yeah, just a quick accident. I mismanaged the clicks on my side and accidentally went out of the session. But I'm here. I'm back. I'm gonna share the customer service desk link right now.
I put it in the chat, Felix. We had just a question
Already,
of
good.
Mr. Ranjit Kumar. If Mr. Ranjit Kumar, if you can repeat your question, please.
Yes, sir. Sir, can we use AI to enhance gate fidelity for superconducting qubits, sir?
That's a great question. I'm sure a lot of people have looked into this. We haven't yet, but that would be a very nice research topic. I think I actually, in the last March meeting, saw some presentations about that kind of thing, but I cannot tell you who actually did this.
Okay.
There are also companies that are specialized in quantum control. There's a company in Australia called Q-Control, QCTRL. They use some AI, I'm sure, to try to kind of optimize the fidelities. But they work at a more hardware agnostic level, as far as I can tell. So higher up the stack, where they don't actually explicitly model the 3D structures like we do. So it's kind of a complementary approach to what we do, I think.
Thanks. Excuse me, can I ask a question? This is Ajay. Is it audible?
Yeah, I can hear you.
Yeah, actually, I want to ask that if you have, say, eigenvalue problem for a, say, Poisson equation where you calculate electron density and couple it with Schrodinger equation, what was the boundary condition in 3 dimension will be there?
Yeah. For the Schrodinger solver.
Yeah, because Schrodinger equation, you have to connect the density. So the boundary condition in the 2 cases where you have electrostatic condition, and on the other side, the Schrodinger equation,
So
where you have a dynamical. Yeah.
We solve it in a 3D domain in real space, and using finite element discretization. And so we use these so-called natural boundary conditions, which will what these natural boundary conditions do is they make the essentially the transverse component. So that if you take the gradient of the wave function at the interface, you take its normal component to the interface, and that is set to 0. Equivalently, in 1D, this would set the derivative of the wave function to 0 at the sides. So you need a dot region that is big enough that the wave function essentially vanishes at those sides for this method to be accurate. You can also, if you want, enforce boundary conditions that set the wave function to 0 by making the surfaces perfect insulators, and then the wave function will be forced to vanish on the sides. But that is not necessarily the right way to do things, because this kind of forces your box to behave like a quantum dot, and you want to know if you have bound states or not. So it's safer to start with to just say like natural boundary conditions and big enough box. Then you have to inspect the wave functions you get, because if the dot region is not chosen appropriately, you may end up with unphysical bound states to the surfaces, and that you want to avoid.
And to avoid the unwanted region, what is the method one has to follow to eliminate those regions?
Yeah, so to eliminate spurious solutions?
Yeah.
Yeah, you can, so this happens, for example, if you have local minima. Suppose I have a quantum well structure, you can have a very deep quantum dot. If it's the global minimum, the solver will find the lowest energy states, so they will always be the bound states. But if on the sides you have, outside the barriers, you have global minima that are even lower in energy than the quantum well you want to study, you may end up solving for energy levels, for wave functions outside the dot region that you don't really care about, and that may not be physical. So to solve this, you have to adjust the dot region to be approximately corresponding to the maxima of the potential barriers, essentially.
Okay, the last very quick question. You said somewhere that there are electrostatic charge and also there is a quantum charge. So we fill that well with quantum charge. So how these two charges will be distinguished?
Okay, so what I call the classical charges are actually simply what you get in a semiconductor at equilibrium. If you solve for the hole density or electron density by assuming that these electrons are occupying plane wave states in a quadratic band, then you can show that the electron and hole densities are given by these Fermi-Dirac integrals of order 1/2. And this will simply be the charges you get at equilibrium in a semiconductor when the conduction band edge, for example, goes below the Fermi level. And you get a lot of those charges. The densities are, if you have strong doping, the densities can be in orders of 10 to the 20 centimeters minus 3. So these are not really like quantum confined. They're just like classical charges. Now, what I call the quantum charges are inside the dot region, you expect to see only a few electrons, actually, a few conduction electrons.
Yeah.
And you can solve for Schrodinger's equation to get the electronic structure of those charges. And then you can solve for the impact of those charges on the reservoirs in various ways. You can do self-consistent Schrodinger-Poisson. I haven't shown it in the simulation, but this can be done. Then you would get the charge density that corresponds to those quantized charges in the quantum dot. The other solver you can use, if you want to very accurately describe a few electrons in the quantum dot, you can solve the exact many-body problem using exact diagonalization solver. This works very well for 2, 3, 4 electrons, for example. We've done up to 10 if you're patient, but of course the scaling is factorial with the number of electrons or holes, simply because it's the full quantum mechanical problem accounting for all the interactions quantum mechanically. But since quantum dots are typically designed for few electron operation, it's very useful. And you can get the exchange interaction very accurately, for example, from this method.
Yeah. Is it possible to solve this problem using Lagrangian action approach, where you have integrals of action kind? Your life will be much better than Schrodinger.
That's interesting. We've never tried it. You could, if yourself, if you want, but we haven't implemented it.
Feynman path integral.
Yeah, that's an interesting approach. We've never tried.
Okay, thank you, Mr. Félix.
I have a hand raised. Abdelali Fargi.
Hello?
Yeah.
You hear me?
Yes.
Yes. I have some experimental results from quantum dot high electromobility transistor showing negative differential capacitance on results. And I want to simulate that this effect on using quantum TCAD. Is it possible?
Negative quantum capacitance? Quantum capacitance, I believe you can get from a Schrodinger-Poisson solver. So you would get the charge densities in the dot using the Schrodinger-Poisson solver, and then you would need to differentiate it with respect to the gate voltages, I believe. You can post something on our support desk, but I think we can address quantum capacitance, yeah.
And what can we what quantum TCAD can offer using as simulations in for quantum computer? What can quantum TCAD offer as simulations
for quantum computer specifically?
Yes.
Okay, it's essentially a way to get the physics to do solve for the physics models that you need to compute parameters that go into modeling the logic gates and the readout, for example. So, for instance, an example I can give you with our many-body solver, you can solve for the exchange interaction strength. So this determines how fast nearby spins can flip and be entangled together. Right? And this is the main resource for 2-qubit gates in spin qubits. So you can use QTCAD to tell you, for a given geometry, given gate biases, how fast will the 2-qubit gates be. That's one example. Another example is this EDSR control. You can calculate how fast the single qubit gates will be when applying a microwave drive on the qubit.
So we can use it in a superconducting qubit system?
For superconducting qubits, I showed an example. We can calculate the capacitance matrices. We can calculate the Maxwell eigenmodes, and these determine the Hamiltonian of the chip, and therefore the behavior of the chip under quantum logic gates. So yes, it can be used for superconducting qubit design as well.
So what's the advantage of QTCAD over cascade metal using EVM?
They are complementary. So cascade metal doesn't have any finite element solver. So cascade metal will enable you to design the chip, but not to solve for its properties. To solve for its properties, you need to use various finite element modeling tools, and QTCAD is one of them.
Okay, thank you. Okay.
We have Ash.
Yeah, sorry, I just wish to ask if this will be uploaded somewhere because there were some things I could not follow.
Sorry, what's the question?
I'm just asking if this would be uploaded somewhere because there were some things I could not follow. That's all I wanted to ask.
I don't know if Anil recorded the session.
Dear participant, yes, we will share the recorded after this session.
Yeah, thank you.
Okay. We have MD Shab, and sorry, I'm seeing 3 dots, so I cannot pronounce the full name. I'm not seeing the full name. MD Shabazz. Okay. We're not hearing you. Maybe you should turn on your mic, or if you're not there anymore, we'll switch to another question.
Participant, any other question, please?
We have King Shook.
Yeah.
King Shook.
Félix.
Yes. Hello.
Okay.
Am I audible?
Sorry. There's already.
Am I audible? Yes. Yeah, very nice presentation. So I have one question. So can one simulate spin transistors using this QTCAD or superconducting spin transistors also? So how to simulate that thing? There are spin transistors like spin field effect transistors where you have spin orbit coupling and Zeeman interaction will be there, and also polarized leads. So how to simulate that thing, and also include quantum dots and various kinds of geometric phases is possible.
Interesting. We designed QTCAD specifically for spin qubits. That being said, it has many solvers that are available and useful. Sorry, it has many solvers that could potentially be useful elsewhere. I'm less familiar with spin transistors. What I can tell you, we do have spin orbit coupling in QTCAD. And we can model quantum dots. We can model single electron transistors using QTCAD as well. I would encourage you to look at our website, look at our documentation, see the features we have, and see if these are helpful for spin transistors.
Okay, I have one more question. So that question is regarding this superconducting qubits. So you said about superconducting qubits can be simulated. I am assuming those qubits are low transition temperature, the conventional superconductors.
Yes.
So how far work has been done for high temperature superconductors?
Very little. Very little has been done. Yeah.
I personally have worked on high-energy superconductors, various materials like Qubits, BISCO, YBC, etc. Some theoretical simulations I have done. So how far or how much work is been done, or how far can be done using QTCAD?
For high-TC superconductors, honestly, I don't know what in the literature. I've not seen much on this topic. It's an interesting research topic. What I can tell you is that for superconducting qubits to work well, it's not only about the critical temperature, it's mostly about the noise, and you get a lot more noise at high temperature regardless of the superconducting state or not, because there are many sources of noise that are simply not related to superconductivity here. So what we have right now in QTCAD in terms of features, capacitance matrix extraction, Maxwell eigenmode extraction, at that level, we're modeling the superconductors as a perfect conductor. I don't see how this would be different for high temperature superconductors. I think this could be done as well, but this is kind of a phenomenological description of superconductivity. If you want to go deep down into superconductivity, you need some more fundamental superconductivity solvers that we are developing right now but don't have yet. In terms of deeper materials physics modeling, if you want to model the Josephson junctions, you can do that with Nanoacademic. That's a different tool I haven't described today, but it's an atomistic software that is available in India through Impulse as well, and that we develop and maintain. And using Nanoacademic, we can model the Josephson junction. And what we do here is we look at the normal state resistance of the junction, and using Ambegaoka-Barata formula, this is related to Josephson energy directly in a way that fits with most experiments. So maybe there's something there in terms of material science that could be done. But yeah, we don't have any example yet specifically for high TC superconductors.
Okay, thank you.